exhibit. Okay, so right, induction. Only the electrons are moving, protons can't. But for the sake of this, I'm going to show a distribution of charge. So it's not a 100% accurate thing. Okay, right here we got soda can. It's chilling. All right, it's chilling on a styrofoam cup, which acts as an insulator. So right now we have one, two, one, two, one, two, one, two. We have neutrally charged metal can. Same amount of protons as electrons, 4 and 4. Now you can't really quite see it too well, but the balloon, all right, that is brought near, negatively charged. So remember, all right, as we were saying, it's the electrons, all right, that have the ability to move. And what do like charges do? And your opposites. Yep. So from here, what are the electrons going to want to do? Guys, what are they going to want to do? Are the electrons are they going to want to move towards the negative or away? So negative wants to move towards negative.
Away.
Good. All right, it's all right. I'm not yelling. I just want to make sure we got that right. So the electrons, they're going to want to go as far to this side as possible. They really don't like all that extra negative stuff right there. So they go to this side. All right, which leaves this side overall more positively charged. All right, seems easy enough. So now, since this is negatively charged, and we've now added a hand here, all right, this hand is going to act as a grounding wire. If you guys remember that, usually we show that symbol as like, okay, here's a charged object. Here's a little wire that goes to the ground, and just as usually our symbol. This grounding is basically a highway for electrons to either go into an object or away from an object to try and neutralize a charge on a specific side. So if we're looking at just this side, if this side was all positive, let's say, if this side was all positive, well, we would gain electrons because they'd be attracted to that. So more electrons would add in, and then we take away the grounding wire. Now we're overall negatively charged because we've added some. Well, if this side was negatively charged because there's a very strong positive charge on this side, these electrons were going to want to try and get away from that positive charge. So some of the electrons would leave. So we'd say goodbye, 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 and then take away the grounding wire, and now we're less electrons positively charged. So that is essentially what is going to be happening here. All right, remember that this side right now is mostly positively charged. This side was negatively charged. So we had some 1, 2, 3, 4. Okay, the electrons, what are they going to want to do? Bless you. Right? Are these electrons, or some of these electrons going to want to leave, or are some electrons going to want to join into this? Very good. They're going to want to leave. Why? Because this negative charge, all right, I'm sorry, I want to retract my statement. If this was positively charged, we'd have electrons enter. If this was negatively charged is when the electrons will want to leave. I apologize for that. So since this is a super strong negative charge, these electrons want to get as far away from this as possible. So because of that, they're going to basically make and use a path, all right, from the hand to the ground. So we lose 1, 2, and now when we take this away, all right, we stop touching it with the grounding hand. Now we would be down, let's just say we lost 2 electrons. Now we take that away. You still have your 4 protons. What's the overall charge? Positive. All right, so that is charging by induction. All right, this is charging by induction. So that is going to be, all right, this first one, E. When the balloon was first held near the soda can, a neutral can. Remember that this is negative. This balloon is negative. So how did the charges move? They went to the other side, right? The negatives went to the opposite end, so we're looking at B. We're looking at B. When the soda can is held by our hand, blank move from blank to blank. Well, can protons move, guys? Nope, so that eliminates A and B. So you're left with C and D. And just look at the picture. If this is a negative, and I add my finger here, right, where electrons can either go in and out, they want to get as far away from that as they can, so some electrons are going to go from the can to the hand. All right, so that's what we're looking at, and that will be letter D, can to the hand. The process, this process causes the can to acquire what was the overall charge on the can at the end? Positive, very good. When the induction charging process is complete, the balloon, what happens to the balloon? Did the balloon actually ever make contact?
No.
So was there any way that electrons could jump one way or the other?
No.
So guess what? Still negatively charged and still the same amount. Now, if it did make contact, we could say that some electrons either jumped in or jumped off, and then there could be like a differing number of stuff. But it didn't. And in general, the use of negatively charged object to charge another object by induction causes it to get the opposite charge. So in this case, positive. Yeah. All right, so now let's take a look at this guy here. Let's take a look at this one. Oh, yep. All right, so same. Here we had a positive, negative. Okay, neutral. This time the balloon has extreme amounts of positive charge. So what's going to wind up happening? The electrons that were neutral and they can move around, are they going to be attracted to this positive charge? Hell yeah, they are. They're going to be like trying to holla at all this positive charge. So these electrons all kind of scoot over here, which leaves the right side more positively charged. All right. Now, again, so this side is now more negatively charged. This side is more positively charged. When we add a grounding wire here, all right, our hand is acting as our grounding piece. Our hand is acting as our grounding piece, where electrons can either move in or move out to try and fix the charge on the right-hand side, or whatever side we put our piece on. All right, so what did we say this left side was? Was the charge on the left side? Well, if this is positive, what do all the negatives want to do? Go closer to that. So this side, negative. What is about this side? Positive. So, if that is the case, right, if this side was all mostly positive, are these extra electrons, are they going to be attracted to that positive charge? Do you think, right? Well, do opposites attract? Yeah. So guess what? Electrons, all right, that are basically can travel up the hand, and then they're going to jump from the hand to the can. Okay, so now we're gonna add in a couple of extra electrons. So we're gonna add in an electron here, and then let's say an electron there. Now, once we take away our hand, what is the charge in the can going to wind up being? Very good. It's going to be negative. And just guys, a quick little trick for that is it's always going to be opposite, all right, to what the charge on the object is that's inducing it. So on the back side, right, we had on the front side, we had this. Okay, we had a negatively charged balloon. Electrons wanted to get far away from it. They yeeted. And so when we took that away, since we lost electrons, this thing was overall left positively charged. That's the opposite of the balloon. On this one, balloon is positive. All right, we have the electrons attracted to this. And now, since this side was mostly positively charged, we had electrons coming from the ground, all right, our path from the hand to this side. We've added some electrons. We take it away. Now the thing is overall negatively charged. So 8 asks basically, what did the charge look like when we brought the positive balloon near it? Yep, good. A. All right, can protons move again? No. Nope. So A and B, goodbye. C and D. C. Good. Electrons move from the hand to the can. This process required the can to get what kind of charge? Negative. All right, so polarization is essentially using induction and grounding. All right, so here we have two cans that have the same amount of positive and negative, positive and negatives. Now, they're touching. The two metal surfaces, electrons can move all around. Some electrons from the right side can jump to the left. Some from the left can jump to the right can. They're allowed to. Now we bring in a negatively charged balloon. If we bring in a negatively charged balloon, what are the electrons going to want to do? Are they going to want to move towards the negative or away? Good, because like charges repel. So since the electrons don't like this, electrons from this side, all right, they're all going to kind of go and try and basically stockpile as much as they can over this way, which would leave the left soda can what kind of charge overall? Good. And now they're basically just going to say, okay, sweet, we didn't actually touch anything, but they're standing on these two little styrofoam cups that act as insulators, so the charge doesn't just leave and go to the ground, so they stay neutral. Right, so yesterday when we were using the Van de Graaff generator, you guys were standing on the books so we could pass the charge around. All right, if not, you stood there, you wouldn't be able to shock anyone because you basically just be, all those extra electrons would just leave you right into the ground. So now they're just taking the two bottoms and separating it. So if that's the case, what is going to be the charge on each can? Okay, so which can would be positive? The left one, yeah, hell yeah, very good. All right, so this can is going to be overall positive charge, and this one is going to be overall negative charge, just like that. All right, and that's pretty much all I wanted you guys to get out of that one. All right, so that's all you guys are going to need from that one. And then now we're going to look at conduction. All right, so here is our charging by conduction and grounding. Again, same thing as the worksheet prior, electrons, protons. Okay, still same rules. Negative charges are attracted to what? Positive, and then negative charges also are going to be repelled by negative, right? They are like trying to get out. So to metal sphere, all right, is touched to a neutral object, and then we see what's going on. So let me just say, all right, what is the process going on here? Is the teacher rub the bar on the metal sphere? So a metal rod rubbed onto a metal sphere? Absolutely not. Just thinking about rubbing like two silver, like a fork and knife together, that little high-pitched screech, that would bother me? Absolutely not. That's not going on. Held the bar near but not touch? No. This is pretty much showing that it's touching. All right, so yeah, bing bong. There you go. Looking at C. So let me draw in what is happening. and I'm going to explain at the same time. So, guys, as this rod was brought near, what's going to happen to all the negative charge in the sphere? Is the negative charge, going to be attracted to the negative, or is it going to be repelled? It's going to be repelled. So all the negative is going to go, they're going to try and go all the way over here, which leaves what kind of charge close to the rod? Positive. So guess what? These electrons here, these electrons that are in the rod are now attracted to this positive part. Some of these electrons are going to jump. Yep, they're going to jump in because they're attracted to this positive charge. So now we've added in an extra couple of electrons. Now we take the rod away. Well, we've just added some extra electrons. Now you see how these electrons are all kind of stuck right here in this spot? Well, do negative charges attract each other? What do they want to do? Repel. So do you think these negative charges here are going to want to stay tight together? So what are they going to want to do? They're going to want to disperse. They're going to want to spread out evenly. So these guys are just rearrange and orient themselves. So even though there's now extra negative charge here, they're going to try and separate and move themselves as far away as possible. So that is what A, B, and C is explaining. So we're not going to read that. So 3. Diagram A, charging step. How does the sphere become charged? Well, how did it happen? How did the sphere become overall charged? What did the electrons do? Well, they moved from the metal bar to the sphere. So we're looking at B. When the metal bar is pulled away in diagram B, now the metal bar is what kind of charge? Okay, well now they're asking about this thing. So did it lose all of its negative charge? No, it lost some, right? So the rod or metal bar is still negatively charged, but it has less excess electrons than it did. Why? Because some of them jumped onto the sphere. In diagram C, all right, shows a completely different charge distribution. Just say that, all right, the electrons repel each other. The electrons repel each other. All right, so that's why they went from being added onto here, and then they were like, yeah, awesome, but now they want to spread all around. They want to go, all right, you go down this way, you go this way, you go this way, you go this way. So we're all kind of evenly spaced out. All right, so that is on that end. Now you have a positive, all right, now we have a positive thing going on here. So a positively charged rod, what's going to happen to the electrons in here? If this rod is positively charged, the electrons in the sphere, are they going to go towards positive or away from positive? Towards it. Towards it, 100%. So they're all going to be like, yo, what up? Holla at your boy, which leaves the right-hand side overall positively charged. Okay, so are we done? No, because it makes contact, the electrons have a path to move. So some of these electrons are very attracted to this super positive charge on the rod. So what happens is some of these electrons, they will jump, essentially. All right, they transfer over to the rod. So we lose some of these electrons. Now we take the rod away, and we're left with an overall positive charge. All right, and then same thing, metals on the metal sphere. Okay, the charge winds up getting evenly distributed. All right, all over. The electrons are able to move around. They kind of help spread everything out, spread all this excess positive charge area here. Okay, so again, that's what A, B, and C is explaining. All right, so yes, some of that negative charge gets in here and it kind of moves everything, keeps it nice and spread out. So in diagram A, the charging step, how did the sphere become charged? Electrons move from the sphere to the positively charged rod or positively charged bar. And then when the metal bar is pulled away, what's happened to the metal bar? What's the charge on the metal bar? It's still positive, but it's got fewer excess protons. Why? Because we added some extra electrons to it. So what is good here? Well, the hand, again, is acting as a grounding wire. All right, so electrons can either jump into, all right, or move away from the charged object. It depends. It all depends. So right now, this has a lot of excess electrons. So if I just touch this thing and provide a path to the ground, what are these electrons going to want to do? All right, if this thing wants to try and neutral itself. So if it has a lot of extra electrons, what do you think is going to happen? Are the more electrons going to want to go from my hand to the sphere, or from the sphere through my hand and down into the ground? Correct. So we're going to lose some of this excess charge, right? It's going to go to the hand. All right, so we lose one or two of these. All right, now we take our hand away. All right, and we are now neutrally charged. The end? No, like an end. Yeah, instead of writing out, I was just showing it with like the overall charge. So like this is an overall excess amount of negative. Now what's going on here? We have extra positive charge. So same thing. Our hand is acting as a grounding path. So if this is overall positively charged, remember the positives can't leave. So if we want to make this thing neutral, what are we going to need to do? Are we going to need to add electrons or lose some? Yeah, we're going to need to add them. So we have electrons basically move from the hand, yep, to the sphere. Okay, so we add in some electrons, and now this was positive, and now it's going to be overall neutral. Heck yeah. All right, that is charging, or that is conduction and grounding combined. So the process of neutralization, all right, the process of neutralizing the charged spheres, as shown above, is known as grounding. In the negatively charged spheres, what happened to the electrons? Well, or what happened? Protons don't move, so C and D are by. Electrons move from the hand to the sphere. Opposite, right? They go from the sphere to the hand, and then right, if this is the rest of the hand, so I don't know how to do that. All right, now they have a path away. And then 10, on the positively charged spheres, again, the protons don't move, so electrons go from the hand to the sphere in order to help, all right, keep the charge overall neutral. So here we have charge interactions. All right, so here we have charge interactions. All right, again with the protons and I'm sorry, protons, electrons. We're not going to freak out about that. Oppositely charged objects. Opposites do what? Likes do what? Repel. And a charged object and neutral object, they will attract. So a neutral object is attracted to either positive or negative. All right, so a neutral can be attracted to either positive or negative. So if I just showed this, positive, negative, yep, they're moving towards each other. Like charges, so positive and positive, they want to go away. Negative and negative, they want to go away. Positive and neutral, they're attracted. And then negative and neutral, they are attracted. Well, can neutral ever repel something? Absolutely not. All right, so we got to want to make sure we add that over here as well. Neutral never repels. Neutral never repels. So right now, all you're seeing is two balloons being attracted to each other. So what can you tell me? It's going to ask, are both of these balloons the same type of charge? Absolutely not. Are both balloons charged with the opposite type? Maybe. You too. Both balloons are charged with either the same type or opposite type? No, that can't be because if they're the same, there would be some kind of repulsion. Only one of the balloons is charged, the other is neutral. Again, that's maybe. You can't know that for sure, but you can tell me that at least one of them is charged and that the other is either the opposite charge or neutral. Hmm? Well, you see how like the both ropes are swinging towards each other, so that's just going to show like some form of attraction. So basically, it could be this, this, or this. Those are the three possible options. As you look around the room, you observe two balloons splitting apart or repelling. Only one option. They have to have the same. Very good. And that would be letter A. And then you have this one here. Hold up. Wait a minute. Something ain't right. No? Come on, you guys seen that like TikTok, yeah? Hold up. Wait a minute. Something ain't right. All right. Well, anyway. All right, guys. There is no indication of anything that we looked at that kind of shows one just chilling and the other being attracted. Doesn't work like that. So it is correct. It is A.
Is it really?
It is. That's nonsense. It cannot happen like that. It will not happen like that. Very, very good. Now we're going to look at number 6. They say that you have little bits of paper on your desk. And the paper is neutral. And then you have a balloon, and they know that the balloon is negatively charged. So, what is the name of the person in number 6?
Analytical.
That's right, analytical. All right, it says that analytical is in a physics lab in which she charges a variety of materials. and tests them to determine their charge by bringing them near a negatively charged balloon and near some neutral paper bits at rest on the table. Help Anna draw conclusions from her observations by entering a positive, negative, or neutral, or a combination of these, if absolute conclusiveness is not possible. Okay, so we have little bits of, let's say we got little bits of paper here, little paper bits. Got little paper bits. So these things, neutral. So what can the neutral guys be attracted to? What can neutral be attracted to? Either or. All right. What can negative be attracted to? Positive or neutral. So these can be positive or neutral, and paper can be attracted to either negative or positive. So object A is observed to attract the paper bits. So let's just say my pen is object A, and these things are, if I hold the pen here, they're attracted to it. So what happens? What happened there? What would the charge on this object have to be? Right, so the paper bits were just attracted to the pen. It could be positive, all right, or negative or positive. All right, it could be either one of those. Now, object B is observed to attract the balloon. Okay, so if this is a little balloon, this little chicken thing. If it's a chicken balloon, okay, and if object B, all right, is attracting to the balloon, all right, is attracting to the balloon. Balloon is negative, so what can we definitely say? Well, we can say that it is positive or neutral. Positive or neutral. What about C? Object C. Object C, I bring it near and it repels. I bring object C near the balloon and it repels. So what does the charge have to be on C? Well, if B is negative, what would repel a negative? A negative. So this one is 100% negative. Now object D attracts, if I bring it near the paper bits, attracts the paper bits and it attracts the balloon. What would the charge then be on that? It has to be positive. Why? Because opposites attract, right? So with as far as the paper bits, all right, it attracted the paper bits, so it could have been positive or negative. But since it also attracted the balloon, that basically tells me that it can't be negative. So it has to be positive. 100% has to be positive. And then E. E is observed to attract the paper bits and repel the balloon. So vice versa, if the paper bits were still here, lost a couple here, so we still have our paper bits. Come on. And object D, all right, object D, we bring them near, and it attracted them, good, and we bring this near the balloon. If we try to bring it here, and it repels it. So what does the charge on object E have to be? Well, it has to be negative. Since it could attract the paper bits, it means it's positive or negative. And then if it repelled the balloon, then it means it has to be negative. It can't be positive. So that is 100% correct. So now we have a couple different scenarios here. All you know for sure is that B is negative. So right off the rip, I bring A here. What could A possibly be? It could be positive. And that's correct. It could be neutral. So A could be positive or neutral. What about C? It has to be negative because it's repelling. So C, 100%, has to be negative. A could be positive or neutral. All right, B is negative. B is negative. What could A be? Positive or neutral. Now, if A we said was positive or neutral, but you see that it's repelling C, then it would have to be positive because a neutral object will never repel anything else. Excellent, excellent, excellent line of thinking. So, yes, all right. You're eating. Is that did I use it right? You're eating this lesson. You're just kicking this lesson's butt. There you go. That's what I like to see. Gotta eat. Now, B we know is negative. What could C be? It could be positive or neutral. So if we said that C was positive or neutral, and you see that it's attracting A,
It has to be negative.
does it?
Well, it could be.
So if A was negative and this was neutral, it would attract.
Yeah.
All right? But if C was positive, A could be neutral, right? And it would attract. So this one could be neutral or negative. Sorry. I didn't mean to get you there. Try to get you on the forearm there. All right. This one, guys. All right. Need your help on this one. Need your help with this on this one because this one's tough. Guys, what's the name of our person in this one?
These are so stupid.
Genius. How dare you? Genius is an amazing name.
Did you come up with it?
Nope, I did not. But I wish I did because that is super clever. All right. Oh boy. All you know for show is, let's see. We know that object A is negative. All right, so Genius knows that object A is negatively charged and that B is neutral. What can Genius definitely conclude about the charges on C, D, E, and F?
Shouldn't they know if they're genius?
Well, who says geniuses know everything?
But if he's a genius, he should know.
Well, maybe they are a genius when it comes to something different. It could be music. They've never picked up an instrument and they can automatically do it. All right? Well, I'm just saying. So
Maybe Anna should have done this one.
So what we're looking to do here is try and determine the charge on each of these guys. So F, E, D, and C. All right, it says that F attracts object A. So what does that mean? F could be either negative or neutral. Now let's see what else. F repels object E. So it has to be negative because it's repelling something. So boom. All right. Wait a minute. I apologize. No, it has to be positive because we said that A is negative. So if F attracts A, it would have to be the opposite charge or neutral. And since it repels E, all right, That means this can't be neutral, and that E would also have to be good, positive, because like charges repel. Now, object E attracts D, so D could either be negative or neutral. But it's telling us that D and C repel each other, so that means it can't be neutral there, that it would have to be negative, therefore so with C. And then they're just saying, okay, well, C attracts B. Well, that would make sense because a negative can attract a neutral. There you go. Excellent job, guys.